Welcome to the September edition of the Liftoff webinar series. Today we're featuring Carpenter technology and their next generation of alloys for defense applications. Before we get started, would like to go over a couple of housekeeping issues. If everyone can please put their phones on mute, that would be fantastic. We are recording this session so we can post it on our website later, and the less background noise we have, the better. So we appreciate that. Also, folks can certainly ask questions. We'll facilitate a Q&A at the end. There's a chat function that you'll see on the as part of the Zoom webcast program. It's either the top or the bottom of your screen, depending on how you're looking at it. But please utilize that. You can address the questions to me, Joe Steele here at Lift, and I will facilitate that Q&A as we go forward. I do want to spend a couple of minutes and tell you a little bit about Lift if you are unfamiliar. Would certainly want to make you familiar. We are, I mentioned, based here in Detroit. We are an applied R&D institute that was set up in 2014 by the Department of Defense. And really our mission is to advance technology and talent development, really drive rapid implementation of smarter manufacturing with a vision of driving American manufacturing into the future. These institutes were set up to really reinvigorate manufacturing across the country and to help fill the skills gap that exists in advanced manufacturing across the U.S. Where we fit in the our original charter and where we kind of fit is in the technology readiness level between 4 and 7, kind of bridging the gap between the early research that's done in government labs and in universities, and really trying to connect that to the private sector. It's the valley of death, as folks will say, where the funding is really strong in the early research stages and really strong when technology is about to be commercialized in the private sector. But that TRL 4 through 7 is where that funding and wanes a little bit. So we want to connect the two and really help bring those early research ideas and technologies forward and help drive them to commercialization. As I mentioned, we are part of a larger network of institutes called the Manufacturing USA Network. 8 of the 14 institutes across the country were supported by and continue to be supported by the Department of Defense, including Lift. There are 5 others established and supported by the Department of Energy, and there is 1 that is supported by the Department of Commerce. You can see the various technologies we all operate in. Our original charter here was lightweight materials, mostly on the metallic side, but you can see there's additive and regenerative manufacturing and advanced fibers, and you can learn more about the Manufacturing USA Institutes at manufacturingusa.com. A little bit more about what we have done over the first 5 years of our existence. We're made up of we're a membership-based organization. We're made up of 200 plus industry research and academic and workforce education development partners. At any point in time, we have had 600 plus engineers and economic developers working on our initiatives. Here in Detroit, we've kind of an open door policy. You're welcome to stop by at any time. We're about a mile or 2 away from downtown Detroit. We've had about 3,000 visitors in the last 12 months to our 100,000 square foot facility that has $20 million worth of metalworking R&D equipment in it. Over the first 5 years, we've reached out and had impact with over 350,000 students and teachers through more than 40 education workforce development initiatives, and we've committed $78 million towards technology projects. Quick snapshot of our membership. As you can see, there's large and small companies along with government partners, and you can see all these folks continually updated on our website at lift.technology. Some of the things that we offer our members, and we don't have to be a member to participate in some of these things, but we are a membership-based organization, as I mentioned, various levels depending on your engagement desires. but we can connect you to government R&D programs. We can connect you to education workforce development products and services, including our brand new LIFT Learning Lab that is here in our Detroit facility. And then there's any number of services that we provide as well. So you can learn more at lift.technology. You can be sure to follow us on Twitter at News from Lift, and you can check us out on LinkedIn as well if you just look us up at Lift-Lightweight Innovations for Tomorrow. Look forward to you all following us there. So in the meantime, I know you didn't come here to hear from me. You came here to hear from Carpenter. So with that, I will turn the presentation over to Colleen Tomasello to carry us through the rest of the webinar. Colleen, the floor is yours.
Thank you, Joe. Welcome, everyone, and thank you for joining us today. My name is Colleen Tomasello. I'm in product development for aerospace and defense at Carpenter Technology. We would like to give you an intro to some of the new products Carpenter has to offer, especially with an interest towards defense applications. So our agenda today is I'll give you a brief introduction about Carpenter Technology. Then we'll go into 3 of our new product offerings. The first will be Dr. Robert Buck, who will speak with us about PyroWare 225, one of our new high-strength alloys. Then I will talk to you about our AirMet family of high-strength, high-toughness alloys that we continue to develop to provide higher strength for demanding requirements like hypersonic applications. And finally, Dr. Richard Grills will provide a brief intro into additive manufacturing. We make many powder products, and our new alloys can also be made by additive manufacturing techniques. So Carpenter Technology alloys are in the stronger, tougher, safer business. We make products needed for critical applications. So it's important that we meet our customer requirements reliably for these challenging applications. Carpenter Technology is a leader in specialty materials and solutions. We have over 130 years of experience, and we provide well over 500 high-performance alloy grades for various strategic markets, including aerospace and defense. These alloys come in various product forms: ingot, billet, bar, wire strip, as well as powder. Today, we would like to focus on our portfolio for defense as we are concentrating many of our efforts in this direction. This picture shows many of our alloys are used in key components for both commercial and military aircraft and rotorcraft applications. Everything from airframe fasteners to engine components, including engine fasteners, landing gear alloys, bearing gear alloys, gearboxes. Yeah, you can see quite a few different alloys are in all parts of the aircraft. And with that, I'd like to turn it over to Bob Buck.
Thank you so much, Colleen. I appreciate that. I'd like to talk to everybody today about our new alloy called PyroWare 225. This alloy is a premium alloy steel, and it offers excellent mechanical properties compared to other alloy steels. It has a relatively lean chemistry, as you can see, only about 0.22% carbon, a little over 2% chrome, 2% manganese, a little less than 1% silicon with about 0.7 nickel and 0.5 rather copper. We also add a little bit of the strong carbide forming elements of vanadium and molybdenum to this grade. It is vacuum arc remelted to give us superior cleanliness. This alloy can undergo a very simple heat treatment of water quenching and tempering. It does not need to be air cooled or oil quenched. Its claim to fame is that it offers an excellent combination of high strength and high impact toughness, as I'll show here in a couple minutes, coupled with very high fracture toughness and very good hardenability. The alloy is weldable, and it is case hardenable by carburizing. It is designed for low temperature use, that is temperatures less than about 600 degrees Fahrenheit, where high strength and high toughness are both needed. We've recently introduced it to a number of industries, and it is finding acceptance as mud motors in the directional drilling market, as shafts and mandrels, as well as aerospace structural components in certain rack and pinion systems. We currently offer PyroWare 225 as a mill heat treated bar or as an annealed billet, whatever the customer would desire. And it's offered from 1 inch up through 10 1/8 inch round. Typical mechanical properties of PyroWare 225. These are given in the longitudinal direction, and all these properties are at room temperature, are given in this slide, where I'm listing 3 different bar sizes, 3.5, 5 inch, and 7 inch, where you can see that the typical yield strength is in the low to mid 180s KSI, with the typical UTS ranging anywhere between the mid 220s to the low 230s KSI. The alloy has good ductility, as seen by its good elongation and reduction of area numbers. But what we're most proud of is the third column from the right, the Sharpie V-notch impact energy, where we're getting, even at these high strength levels, very good impact toughnesses ranging from the mid 50s to the mid 70s in foot-pounds. Hardness ranges typically between 45 and 47 Rockwell C, and we get good grain sizes. Even in the larger size bar of 7 inch, we're still getting 6.5 inch ASTM grain size number. Now this alloy is included in ASTM A579 as grade 85, as I've given those minimum properties in the bottom row. So in this graph, what we've done is we've plotted the 0.2% yield strength versus the Sharpie V-notch impact energy of PyroWare 225 and compared that to other alloys that you may be familiar with, including 4330 plus V and our own custom 465, given 2 different heat treatments. The pink squares given in the upper left of the diagram are the 4330 plus V that have been heat treated for aerospace applications, that is a relatively low temperature. And as you can see, it's giving that alloy fairly high strength, yield strength between about 194 and 200 KSI yield. But the price you pay is relatively low toughness at only about 20 to 24 foot-pounds. If we temper that alloy at a higher temperature to increase the toughness, that data is given as the red squares in the center part of your diagram. You can see that the toughness increases to about roughly 54, 55 foot-pounds, but the yield strength falls to the mid 160s. Our custom 465 alloy, given an H1100 or H1050 age, are given as the blue dots, either the dark blue as the H1100 or the light blue H1050. But you can see that the trade-off is fairly typical in these structural type steels, where you're either offering high yield strength and relatively low toughness, or high toughness and low yield strength. What we're excited about with PyroWare 225 are the green diamonds given circled, as you can see, where we're offering both high strength and high toughness in this grade. If we heat treat it a certain way, the light green diamonds are indicated as PyroWare 225 high tough, where we're able to reach 106 foot-pounds of impact energy and a yield strength of about 178 KSI. We think that the reason for the dramatically increased impact energy is due to microvoid coalescence, which we see quite often on the fracture surfaces of the failed Sharpie V-notch samples. So this is a tempering curve for Pyroware 225. On the left y-axis, I'm plotting the 0.2% offset yield strength. That is given as a red triangle. On the right y-axis, I'm plotting the Sharpie V-notch impact energy at room temperature. That's plotted as the green diamonds. And the x-axis shows the tempering temperature. For all of these data, what we've done is we've taken water-quenched Pyroware 225 that had been austenitized at 1600 Fahrenheit, water-quenched, and we tempered at the various temperatures along the x-axis. As you can see on the left-hand side, we get the highest strength and the highest toughness tempering at 450 degrees Fahrenheit. And as we increase the tempering temperature, we see a monotonic decline in both the yield strength as well as the Sharpie V-notch impact energy. That's why I said in an earlier slide that this alloy is designed for temperatures of operation that are at 600 degrees Fahrenheit or less. At 600 degrees Fahrenheit, we're still able to offer, after tempering at 600 degrees Fahrenheit, approximately 177 yield strength and impact toughness of about 40 foot-pounds. Both of those values continue to decline if the alloy is tempered at temperatures greater than 600 degrees Fahrenheit. We've looked at the effect of long-term exposure at modest temperatures, in this case 300 degrees Fahrenheit, where we've exposed the quenched and tempered Pyroware 225 to times up to 1,000 hours at 300 degrees Fahrenheit, and then pulled tensils and broke Sharpies at room temperature to see what the effect of that long-term exposure was. As you can see, the red triangles, again, illustrating yield strength. Along the x-axis are the log of exposure time from 1 hour up to 1,000 hours. And as you can see, the yield strength is unaffected by this long-term exposure at 300 degrees Fahrenheit, where we're still getting at least 180 KSI yield strength. We were pleasantly surprised to see what the effect of the Sharpie V-notch impact energy was on this long-term exposure, as evidenced by the green diamonds, where even after 1,000 hours at 300 degrees F, our room temperature Sharpie V-notch impact energy was at 85 foot-pounds, greater than what it was when we started at about 60 foot-pounds. We've looked at ductile to brittle transition temperature behavior of Pyroware 225, both in the longitudinal and in the transverse orientations. This image shows both. The red dots are in the longitudinal orientation and the blue diamonds are in transverse. The takeaway here is that even at very cold test temperatures of minus 40 degrees Fahrenheit, we're still in the mid to upper 20s in terms of impact energy, and that's in the transverse orientation. We've looked at the fracture toughness of Pyroware 225. Given our standard heat treatment, we've looked at both longitudinal and transverse orientations. And unfortunately, the material was too tough for us to have generated valid K1C numbers. So I have to report KQ values here. Those KQ values range in the low 150s to the upper 150s, given our standard heat treatment in terms of KSI root inch. Whenever we do that high toughness heat treatment that I made reference to a few slides ago, in the transverse orientation, we're at 173 KSI root inch for the KQ value. The fact is, Pyroware 225 is too tough to determine the true and valid K1C values given the minimum specimen size needed, which is very large, to perform valid K1C fracture toughness testing. We've looked at both gas carburizing and vacuum carburizing this grade. In this instance, we've gas carburized using a 1% carbon potential. The various colors of data that you see in the upper right, AD, AS, ND, and NS, simply indicate if it has an A, we did an intermediate austenization after we carburized and before we tempered. If it has an N as the first digit, as the orange and the green dots indicate, that means we did not give it an intermediate austenization. D and S in the second digit simply mean the material was either double tempered or single tempered. So we looked at these different variants at a number of different tempering temperatures. I'm showing 550 in this particular instance in the interest of time. But you can see that regardless of the variant, whether it was given an intermediate austenization or not, whether it was single tempered or double tempered in this instance at 550 degrees Fahrenheit, we're still able to get surface case hardnesses that range from about 60.5 up to 62 Rockwell C, and an effective case depth, that is the depth at which the hardness falls below 50 Rockwell C, of approximately 60 thousandths of an inch or 1.5 millimeters. In this slide, we show actual core mechanical properties, again, typical and in the transverse orientation, taken at room temperature, for those 4 variants that I just made reference to, where we gave it an austenization before tempering, or we did not, and either single or double tempering. What you can see here is that if we do give the material an intermediate austenization after carburizing but before tempering, it does result in slightly higher yield strength and ultimate tensile strength versus not giving it an intermediate austenization. In all cases, however, the core properties are showing very good ductility and very good Sharpie V-notch impact energy. Case hardnesses are given as the second column from the right, and the case depth are also given in the far right column. This is a typical microstructure after gas carburizing. That Vickers indentation was taken at 5 thousandths depth or 127 microns depth. The surface is given on the far left side of this micrograph. Microstructure looks very good. We've also vacuum carburized Pyroware 225, and we've got similar results. A peak hardness in the case of about 62.8 Rockwell C, and an effective case depth, again, of about 1.5 millimeters or roughly 60 thousandths depth. So to summarize, Pyroware 225 offers both high strength and high impact toughness. It undergoes a very simple heat treatment of water quenching and tempering. It exhibits significantly better properties versus 4330 plus V in the high tempered condition. That is, Pyroware 225 offers 25 KSI higher yield strength, that's a 15% improvement, and 50 KSI higher ultimate tensile strength, that's a 28% improvement vis-a-vis 4330V. At the same time, we're able to offer about 20 foot-pounds or 40% greater impact toughness compared to that workhorse alloy steel. Pyroware 225, as I've shown, offers excellent fracture toughness. The surface can be case hardened by carburizing, and the material is available as mill heat treated bar in the quenched and tempered condition or annealed billet. We've shipped over 150,000 pounds of bar and billet to date in sizes ranging from 1 inch to 10 1/8 inch diameter. Thank you all very much for your attention. I'll be happy to answer any questions if anybody has any. If not, I'll hand it back over to Colleen.
Okay, I will talk to you about the Airmet alloy family. Airmet provides a unique key combination of ultra high strength and high toughness. When you go back into the early alloy high strength steels, 4340 with modification to make it higher strength, 300M evolved for landing gear applications up to 280 tensile strength. But as higher demand for higher toughness came about in the 1960s, Republic developed HP 9430 and HP 9445. But now you're looking at increasing the alloy content as well as increasing the cost. But as demands increased, you have the other alloys that developed, the AF1410s, the Mari Jings, and the Airmet series. And if you look at the next slide, it shows the alloy compositions and how adding nickel and cobalt and moly provide extra strengthening. And as we discussed, that also provides added cost, but that added cost provides very key strengthening elements. If you go to the very next slide, we can talk about how those chemistry differences provide the added high strength. The original 4340 and 300M are just quench and tempered alloy with high carbon lath martensite. Your strengthening mechanisms are just iron carbides and alloy carbides. As you go up adding nickel and cobalt, you get higher strength. Going into the Mari Jings and the Airmet alloys, you've got intermetallic phases, and the Airmets provide us our M2C carbides for additional strengthening. In the next slide, talk about the Carpenter Airmet alloy family. Airmet 100 was developed back in the 1980s, developed for military applications to replace 300M because it has the high fracture toughness that was needed. Has very key combination of strength and toughness, but as demands increased, Airmet 310 came about for added strength. Additionally, we went up to Airmet 340 trying to get into armor alloys for additional high strength. Now, as demands increase once again for higher strength, we're working on the Airmet 360. As you can see on the next slide, Airmet 100 is in many military landing gear applications. On the next slide, it's even in applications for other high performance applications. Airmet 310 is also in connecting pins in military applications as well as other high performance applications as well. As an overview, Airmet is premium double vacuum melted, that's VIM bar. It has the ductile iron nickel cobalt lath martensite that we talked about earlier with the M2C carbides for additional strengthening. It's got very high toughness at each given strength level. The high strength allows for the smaller design. In addition, Airmet provides great formability and good weldability. And right now, actually, we have a new program to demonstrate that in some newer Airmet alloys. The typical strength or typical microstructure is shown. There's the nickel cobalt lath martensitic structure. And to go more specifically into the strength and the toughness of each alloy, Airmet 100 has the 280 UTS, nice strength or nice toughness. Airmet 310 kicks it up a notch. Of course, as you can see, as we kick it up a notch, the toughness goes down. Right now, we're working on the Airmet 360. It's got nice 360 KSI strength. We're working on the toughness. Right now, it looks to be in the 20 to 25 range, but we're trying to optimize that as best as possible. Also, the Airmet alloys have great fatigue performance. You can see compared to the other alloys we've discussed earlier, it far exceeds fatigue performance because of its unique strength and toughness. Now, when we talk about toughness, you can't compare the titanium alloys to steels without taking into account the differences in density. Specific strength is UTS divided by density. So if we put those on the next graph, You can see where specific strength versus toughness, the AirMet family far exceeds all the other alloys that we've been discussing. Likewise, when you talk about damage tolerance, which is very critical in all the applications that are needed for aerospace and defense, AirMet once again exceeds most of the other alloys. In summary, when it comes to, on the next page, in summary, when it comes, the world's toughest applications need the world's toughest alloys. So our solution, the AirMet alloys. When you have a need for strength and toughness and have the real estate to trade, AirMet can provide you the important boost that you need. And with that, I'd like to turn it over to Dr. Richard Grills.
Sorry about that. My phone took the opportunity to struggle to get off mute. Good afternoon, everybody. My name is Richard Grills. I'm the Director of Applications Engineering at Carpenter Additive. I'm going to take a few minutes to switch gears a little bit and talk about additive manufacturing, and particularly alloys for advanced applications. So metal, we deal with metal additive manufacturing here at Carpenter. As you've heard, we're a metals company. And the growth in metal additive manufacturing over the last, particularly 10 years, has got a lot of interest within Carpenter. And as many of you will know, if you're familiar with additive manufacturing, there are a lot of potential benefits in defense applications. There's a lot of designs that are enabled by additive manufacturing. The fact that it can make relatively low volumes of parts effectively is very valuable. But a big challenge exists and remains in additive manufacturing, which is, to gain the benefits from additive, you're often looking at a new design. So making the same old part that you might have cast or forged by additive often gives you no benefit at all. Might as well just stick with a conventional manufacturing process. You often are interested in using a new material, maybe one that you couldn't conventionally produce, which gives you some performance benefit. And then, of course, if you're switching to additive, you're looking at using a new production technology. So you've got three things coming together: design, material, and production. And getting all of those qualified and certified at the same time can be very challenging. So one of the, if you want to go on to the next slide, please, Joe, one of the big things at Carpenter is recognizing that all of these things are interrelated. And to be, say, a good powder supplier into additive manufacturing, we have to really understand the process very well. So over the last few years, we've put together a number of facilities, technologies, and capabilities to be able to really go all the way from application requirements in additive through feedstock supply, lifecycle management, and all of the things around that hex there, including areas which typically haven't been particularly strongly addressed in additive manufacturing, such as post-processing. How should a part be heat treated? Should it be hot isostatic pressed? Should we use conventional heat treatments, or should we use a different heat treatment for an additive part? So putting all those things together with production in the center of the hex there in the middle of the slide, to be able to be effective in producing additive parts, you've really got to understand all of those pieces that go into it. Next slide, please, Joe. So we've put three facilities together. On the left there is the Tech Center in Reading, Pennsylvania. That's where we do our early stage R&D, and we have a variety of laser powder bed fusion, DED, and binder jet machines, and an incredible resource in the 75 metallurgists who work there in the R&D center in Reading. Over on the right is in Camarillo, California. That's a production shop which is using E-beam and laser powder bed fusion technology with NADCAP and AS9100 certified, and principally making parts that go into space applications there for the industry in Southern California, also in oil and gas and other areas in production. The facility in the center is busy taking shape, and it will be opened here in the next couple of months, the Emerging Technology Center in Athens, Alabama. And there we're going to have the full solution under one roof. So we have an atomizer in one corner, a large atomizer that's producing metal powder every day. And then we have the AM machines, HIP, heat treat, finish machining, inspection, and so on, that we can go from powder to part under one roof using AS9100 certification and other certifications to produce high quality parts where we have control over every aspect of the production process. And for aerospace and for defense applications, we see that as a real advantage to just have control over the supply chain and be able to do everything in one place with very strict quality controls. Joe, if you want to go to the next slide. And this is really built off our powder production and wire production facilities, which are in various places around the world. But we have one of the largest installed capabilities for producing powders for AM and for producing wire for AM. Most recently, we added on the right there what used to be called LPW in Liverpool in the UK, who we acquired, it was actually just about a year ago, and they're a very important part of our overall strategy to be world's leading supplier of powders and wire into the AM marketplace. Next slide, please, Joe. So just a couple, these are just a couple case studies, just a few slides, in fact, just one slide on custom 465 and a couple on titanium. But as a metallurgical company, one of the things we're particularly interested in is developing new materials, developing the right materials, qualifying the right materials for additive manufacturing. And this alloy, custom 465, is a conventional material which is developed by Carpenter and is sold as bar and sheet and so on. And it's really an extremely high performance stainless steel, extremely high strength, great toughness, great corrosion properties. And it's really a very premium product in the conventional marketplace. And so in many cases, it would be more expensive than the 304 than the 316. So it might not be chosen. In additive manufacturing, the cost drivers are a little different because processing tends to be expensive. And so spending a little bit more on the raw materials that go into the powder really doesn't change a whole lot about the overall cost structure. And so with custom 465, we have a lot of interest in being able to use this to replace a wide variety of stainless steels with just one material. The advantages of going to one material, as shown, some of them are shown there on the left, just the simplification, reducing qualification costs, which as mentioned can be extremely expensive. If you've got to qualify 316 for one component and qualify 17.4 for another component and so on, why not just use one material, make all the components out of that? Yes, it may be slightly more expensive to buy the powder, but what you gain in qualification costs and you gain in simplification more than offsets it. Eliminating cross-contamination is a huge deal in additive manufacturing, and being able to have one material in your facility is immensely important. So this is an alloy which is being released at the moment, is now available for assessment by companies, and again, to simplify the stainless steel landscape, have one material that can cover all of those applications. If you want to go to the next slide, Joe. So on Ti-6-4, this is really one which exemplifies what I was talking about a little earlier, where really you need to understand the entire processing chain to be able to be good at additive manufacturing, get the most out of it. So Ti-6-4 is a powder that we produce. We use our machines to make parts out of Ti-6-4. It's a very popular alloy. We have electron beam melting machines, which are making parts from Ti-6-4 every day. Works very well, but the strength tends to be a little lower out of an electron beam melting machine. So for many aerospace applications, it's not quite good enough. On the laser powder bed fusion side, typical Ti-6-4 materials can tend to crack in certain circumstances. So again, it can be challenging with some geometries to be able to make a part that has the strength you need and yet doesn't crack. And so when we looked at this problem a couple of years ago, we realized that there was no one answer to solving this problem. It really needed a holistic approach with the powder, process parameters, heat treatment, and design to be able to address this problem, to be able to make Ti-64 components on either a laser powder bed fusion machine or an electron beam machine, which don't crack and which have sufficient properties to meet whichever ASTM or other standard needs to be met. And Joe, if you want to go to the next slide. So this is just some example properties that we've achieved out of this, again, this holistic approach, looking at everything to be able to get the right properties. And so either from electron beam or electron beam or laser powder bed fusion, whether as printed, stress relieved, heat treated, or HIPed, we're able now to achieve extremely good mechanical properties, which are meeting normal industrial specifications for Ti-64, and again, being able to make complex components with I would say at least a vastly reduced probability of cracking, if not eliminated in many cases. And again, how do we do that? It's the holistic approach, understanding the entire process chain, the heat treatment, how to specify the powder, and so on, to be able to do that. So in summary, what we're really trying to do at Carpenter is look at the entire additive manufacturing value stream from the initial application through producing the powder, process parameters on the machine, heat treatment, and so on, and tailoring solutions so that we can meet industrial needs, particularly in aerospace, particularly in defense, but in other areas too, to really enable the additive manufacturing to be much more widely used, become a much more stable and standard production process, really proliferate the technology. I'll turn it back over to, am I turning it to Joe or to Colleen?
That's fine. This is Joe. You can turn it back to me. I want to thank the participants and encourage everyone. If you do have questions, I did send everyone a note using the group chat function. You can certainly use that to address any questions to the presenters, and we can facilitate that now. I also want to encourage everyone to visit Carpenter Technology on their website and follow up directly with Colleen or Dan. You see their contact information listed on the page here. So I would encourage anyone that would like to follow up with them afterwards to please do so. Colleen, did I miss anything, or I jumped in there? But I want to see if you.
Yeah, that's quite all right. I think it was on the summary slide anyhow, so that works. Just wanted to emphasize that we designed for stronger, tougher, and superior performance for our next generation of materials, things like that are required in hypersonics. We've got a lot of new alloys on the horizon as well that were shown in the previous slide that we hope to be introducing very soon. So thank everybody. I thank you all.
Yeah. Again, if you do have any questions, please use the chat function. I don't have really any questions at the moment, but please, if you do have questions, follow up with Colleen and Dan. And she mentioned Hypersonics as a Department of Defense sponsored institute. We know how important that is to the DoD and the warfighters going forward. So Carpenter is doing some important work as it relates to that area. So, if there are no questions, we can certainly wrap it up for the day. I would like to thank our presenters. I want to thank Carpenter. I want to thank Colleen, Bob, and Richard for their presentations today. And folks, you can revisit this webinar on our website in the next day or two at lift.technology. You can find it under the Liftoff webinar section, and be sure to follow us as well as Carpenter on the social media outlets that we have available. Both on Lift is available on Twitter at News from Lift and LinkedIn at Lift Lightweight Innovations for Tomorrow. Well, I think that will wrap it up, and please stay tuned to your emails for our next webinar presentation coming up in October. And thanks again to Carpenter for participating today. And thanks to each of you for joining.